We're looking at the quadratic formula today. So the quadratic formula is the fourth method that we've learned to solve a quadratic. So the four methods that we can use to solve any quadratic, ax squared plus bx plus c is equal to whatever number it happens to be. Typically 0 is what we'd want. So I'm going to write this in function notation. We could graph it and look for the coordinates on the graph. So for instance, we have our parabola. Most of the time our answers are going to be the ones that cross our x-axis here, but we could look for any coordinate point on the graph. We could try to factor it, where our quadratic boils down to like an x minus 2 and an x plus 5 equals 0, and then we use our zero product property to get our answers. We could try to complete the square, where we turn our quadratic into vertex form and then solve for x by getting it by itself using our inverse operation. So, the first thing we would do is subtract whatever this number is, and then we would divide everybody by a, so on and so forth until x is the only thing left. And the fourth and final method we are talking about here in this video is the quadratic formula. The heck is it? There it is. Quadratic formula. It looks pretty intense when you first see it, because you got this x, it's a big fraction, there's a square root, there's this plus or minus sign, a bunch of just letters A, B, and C's. It all stems from standard form of a quadratic, like this. A is the same A here and here. B is there and there. C is right there. The 4 is a part of the process, as well as the 2, from taking it from this standard form, getting us into our quadratic formula. The song that helps us remember, I'm going to sing it here once, goes, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Using that, we can find our answers to pretty much any quadratic that we come across. The discriminant is the stuff that we have underneath the radical. So it's this stuff right here, the b squared minus 4ac. It tells us the root type. If the discriminant is positive, we have two real roots. If our discriminant equals 0, we have what's called a double root. And last, if it's negative, we have no real roots. If you study it further, we actually have two imaginary roots. But for us in Algebra 1, we're not going to concern ourselves with what those imaginary roots are. We're going to keep it simple. If we have a negative discriminant, we do not have any real roots to find. So let's try it with our very first problem right here. I've got my quadratic formula off to the side to help us. The very first thing that we want to check for, are we in standard form? And do we have it equal to 0? Yes to both of those, standard form and equal to 0. We're going to check the discriminant first. Right out of the gate, I want to check the discriminant. So A is the number in front of x, B is the number in front of x, or A is x squared, B is in front of x, C is its lone constant number. So we take 7 and square it. We're going to take 4 times 1 times 6. That's 49 minus 24, which is 25. That is greater than 0. We've got ourselves two real roots. We're now going to use the quadratic formula to help us find it. So we're going to go x is equal to negative b plus or minus the square root b squared minus 4ac all over 2a. And we're going to plug in for a, we're going to plug in for b, we're going to plug in for c. B is 7. I need negative b. So we get a negative 7 plus or minus the square root. Now instead of plugging back in for b squared minus 4ac, we've already calculated it over here. We're not going to recalculate it. All over 2 times a, well a is 1, so 2 times 1 gives us 2. We now move on to simplifying this answer. We can take the square root of 25, so we take the square root of 25 and get 5. We still have the 2. Every quadratic has 2 answers, so this gets split into x equals negative 7 plus 5 over 2, and it gets split into x equals negative 7. Whoops. So negative 7 plus 5 over here is negative 7 minus 5 over 2. With the problem on the left, negative 7 plus 5 is negative 2 over 2. So x is negative 1. Or this side we get negative 12 over 2, and we get negative 6. There are our 2 answers for the quadratic formula. Let's try one that doesn't have a equal or a perfect square underneath the radical. So let's take this one, for instance. First things first, do we have it in standard form? It is, but it's not equal to 0. But lucky for us, since it's just the letter y, we're allowed to change that y into any number that we need it to be. We need our function to be equal to 0, so we set it equal to 0. Check our discriminant, b squared minus 4ac. So b squared is 25. We get minus 4 times 2 times negative 6. So that's 25. Negative 4 times 2 is negative 8. Negative 8 times negative 6 is positive 48. Add that together and we get 73, which is greater than 0. 2 real roots. Time to use the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Plugging in the numbers that we know. B is 5, so I get a negative 5 plus or minus the square root. We've already calculated it. It's 73 all over 2 times 2, which is 4. We now simplify anything that we can. We check, can we simplify our square root of 73? Well, it's not perfect, so we're going to see if any perfect squares go into 73. 4 does not, 9 does not, 16 does not, 25 does not, 36 does not, 49 does not, and 64 is the last possible one before we get 81, which is larger than 73, which definitely doesn't go in there. So no perfect squares go into 73. This is as simple as we could possibly make this answer. Now the last one we're going to do for this video here. Let's see if this is what I want it to do. Should be fine. We're going to set it equal to 0 just like we did the last problem. X squared minus x minus 4. I'm going to check our discriminant, b squared minus 4ac. b squared, so b is this negative 1. Negative 1 squared is 1. Minus 4 times 1 times negative 4. Write that a little bit better. Negative 4 times 1 is negative 4 times negative 4 is positive 16 plus 1 gives us 17. So we're able to use our quadratic formula after all. Plug in the numbers that we know. Well, it's a negative b, so this negative 1 goes right here, so we get a negative 1, which is simply just 1. Underneath our radical, we have the 17, and then we have 2 times 1, which is 2. We check again, can we simplify the 17? 4 doesn't work, 9 doesn't work. The next one will be 16, which we know doesn't work, and then 25, which definitely doesn't work. Ends our problem right there. So what if we've solved our quadratic formula and we get down to a problem that looks like this? 6 plus or minus the square root of 12 all over 4. We go to check to see if we can simplify our square root. We see that 12 is not perfect, but we notice that 4 is a factor of 12. Well, we take our square root, we break it into our two factors, 4 times 3. We are able to square root this 4. It's able to escape the square root right here, and we have 6 plus or minus 2 root 3 all over 4. We're like, yes, we simplified that square root. We're good. We're done. Unfortunately, we're not quite as simple as we could be. This 6, this 2, this 4 right there, they're all divisible by 2. So we are going to divide each one of these numbers by 2 to bring us to our simplest answer of 3 plus or minus the square root of 3 all over 2. Now you might have a question. Why didn't I have to worry about the 3? The 3 is not even. Well, the 3 is protected by the square root. We are not able to get to this 3 on the inside. So the 2 kind of acts like its shield. The 4 and the 2 cancel each other out, protecting the 3 even more with that square root symbol. There is technically a 1 for our final answer right there, but no, we do not have to write the 1 to be considered formally correct. And that is the quadratic formula.